The next ConvNet-based model we shall be discussing is the EfficientNet. This paper, entitled Rethinking Model Scaling for Convolutional Neural Networks, was developed by Tan et al. Of Google. Now, convolutional neural networks are commonly developed at a fixed resource budget and then scaled up for better accuracy if more resources are available. In this paper, we systematically study model scaling and identify that carefully balancing network depth, width, and resolution can lead to better performance. Based on this observation, we propose a new scaling method that uniformly scales all dimensions, that's the depth, the width, and the resolution, using a simple yet highly effective compound coefficient. We demonstrate the effectiveness of this method on scaling up mobile nets and rest nets, which we've seen already. To go even further, we use neural architecture search to design a new baseline network and scale it up to obtain a family of models called EfficientNets, which achieve much better accuracy and efficiency than previous ConvNets. In particular, our EfficientNet B7 achieves state-of-art, that's 84.3 on the top one accuracy on ImageNet, while being 8.4 times smaller and 6.1 times faster on inference than the best existing ConvNet. Our EfficientNet also transfers well and achieves state-of-the-art on Cypher 100, that's 91.7%, and this other dataset, the Flowers dataset, and 3 other transfer learning datasets. We are still to talk about transfer learning in this course, but it should be understood that transfer learning is about training a model in one dataset, say ImageNet, and then using those trained weights as initialization for training in another dataset or with another dataset, say Cypher 100. And we shall get into details subsequently. Now, unlike regular ConvNet designs, as we have been seeing, that are mostly focused on finding the best layer architecture, model scaling tries to expand the network length, width, and resolution without changing F. Now, the authors have defined a ConvNet right here as a function y of I, which is equals f of I, which takes inputs x of I, where f of I is the operator, y of I is the output tensor, and x of I the input tensor. So actually, what the authors of this paper are trying to say is that when building a ConvNet, we don't have to stress on always modifying or changing this function f of I each time we want to modify the accuracy or increase the accuracy or even reduce the accuracy. All we need to do is just to tune some parameters, just a few parameters, and then we are able to increase the accuracy or reduce it depending on the kind of environment in which we are deploying the model. So by fixing Fi, model scaling simplifies the design problem for new resource constraints, but it still remains a large design space to explore the different LIs, CIs, HIs, and WIs. Now, Li here simply signifies the number of layers in which, or the number of layers contained in our ConvNet. And as we had seen previously, with models like the ResNet, for example, we're able to go very deep, that's go up to even 100 or even thousands of layers while maintaining an increase in accuracy. For the C right here is the width of the model. So, and then H and W are the heights and widths of the input image or data, which is the resolution. Then in order to further reduce the design space, we restrict that all layers must be scaled uniformly with constant ratio. Our target is to maximize the model accuracy for any given resource constraints, which can be formulated as an optimization problem. So here we're trying to maximize the accuracy such that we have this fixed convolutional base model and that the memory we are using is less than the target memory, and then the number of operations we are carrying out is less than the number of target operations. So as we've seen earlier, we can increase the accuracy of a model by simply increasing its depth. that's increasing the number of layers. So scaling network depth is the most common way used by many ConvNets. He et al., Wang et al., ZZD et al. The intuition is that deeper ConvNets can capture richer and more complex features and generalize well on new tasks. But however, deeper networks are also more difficult to train due to the vanishing gradient problem. Although several techniques such as keep connections, that's of ResNet, He et al. Is ResNet, and batch normalization by ZZD et al. Alleviate the training problem, the accuracy gain of very deep neural networks diminish. Now for ResNet, 1000 has similar accuracy as ResNet 101, even though it has much more layers. So as you could see clearly from here, the authors are trying to tell us that even though the ResNet comes to solve this problem of vanishing gradients and enables us go even deeper, there are always limits. As we can see clearly, if the ResNet 1000 has similar accuracy to ResNet 101, then it means at a certain point the accuracy kind of plateaus. The next method for scaling up networks is by increasing their width. That is actually by increasing the channels in the different layers which make up the model. Then, as discussed in this paper, wider networks tend to be able to capture more fine-grained features and are easier to train. However, extremely wide but shallow networks tend to have difficulties in capturing high-level features. The empirical results in figure 3 shows that the accuracy quickly saturates when the networks become much wider than W. Here we have the figure 3. We see how as we continue increasing the different values of W, the accuracy plateaus, although the number of flops continue increasing. And it's a similar situation with the depth and the resolution. Talking about the resolution, it says here that with higher resolution input images, ConvNets can potentially capture more fine-grained patterns, starting from 224 times 224 in early ConvNets. Modern ConvNets tend to use 299 times 299. So these are images which come as 299 times by 299 by 3 for better accuracy. Recently, GPipe, that's this paper, achieved state-of-art ImageNet accuracy with 480 by 480, and higher resolutions such as 600 by 600 are also widely used in object detection ConvNets. Now, figure 3 shows the results of scaling network resolutions. And as we had seen, as we keep on increasing these network resolutions, there comes a time where the accuracy actually gets to plateau. The above analysis leads us to the first observation, that is scaling up any dimension of network width, depth, or resolution improves accuracy, but the accuracy gain diminishes for bigger models that actually plateaus. Now, the method introduced by the authors of this paper is compound scaling. So instead of width, depth, or resolution scaling, they propose compound scaling. We empirically observe that different scaling dimensions are not independent. Intuitively, for higher resolution images, we should increase network depth such that the larger receptive fields can help capture similar features that include more pixels in bigger images. Then to validate these intuitions, we compare width scaling under different network depths and resolution as shown in the figure 4. So this figure and this figure. So when we fix the values for the depth and the resolution and then keep on increasing the width, we see how we obtain these 3 different curves, which show clearly how modifying the width while considering different depths and resolutions can actually help in increasing the accuracy or in dropping this accuracy. We'll see how we get the optimal or highest possible accuracy when we select a depth of 2.0 and R, that's resolution of 1.3. When we talk of depth of 2.0, is with respect to a base model. And as it said here, the first baseline network that is when D equals 1.0 and when R equals 1.0, has 18 convolutional layers with resolution of 224 by 224. While the last baseline, that is when the depth is 2.0, it means we multiply this by 2. So we have 36 layers, and then when R equals 1.3, we multiply this by 1.3, hence giving us 299 by 299 resolution. So the second observation is that in order to pursue better accuracy and efficiency, it is critical to balance all dimensions of network, that's the width, the depth, and resolution during ConvNet scaling. In fact, a few prior works, that is Zoff et al., have already tried to arbitrarily balance network width and depth, but they all require tedious manual tuning. In this paper, we propose a new compound scaling method which use a compound coefficient phi to uniformly scale network width, depth, and resolution in a principled way. So what the authors are trying to say here is they are developing this method, this compound scaling method, in which we can now optimize our model by increasing the depth, width, or resolution, but in a more controlled way. So we define here the depth, which is D of the network, as alpha to the power of phi, width beta to the power of phi, the resolution, which is gamma to the power of phi. And all of this is done such that alpha times beta squared times gamma squared is approximately equals 2. We have alpha greater than 1, beta greater than 1, and gamma greater than 1. Now the choice of us having a beta squared and not an alpha squared is simply because this alpha is related to the depth, the beta, the width, the resolution, and gamma with the resolution. And we already have that D, W squared, and R squared are proportional to the number of operations in a regular convolution operation. So doubling the network depth will double the number of operations since it's directly proportional to D, and then doubling the network width or even the resolution will increase the number of operations by 4 since they are actually having the square right here. So if we have to increase the number of operations by increasing the depth, the width, and the resolutions simultaneously, then this increase will be proportional to alpha times beta squared times gamma squared to the power of phi, since this is the same as alpha to the power of phi times beta squared to the power of phi times gamma squared to the power of phi. Or you could better put this as alpha to the power of phi times beta to the power of phi squared times gamma to the power of phi squared, since beta to the power of phi is the width and then gamma to the power of phi is the resolution. And so fixing or constraining this alpha, beta, and gamma parameters such that we have alpha times beta squared times gamma squared to be approximately 2 is the same as saying the increase in the number of operations will be proportional to 2 to the power of phi, since alpha, beta squared, gamma squared is equals to or approximately equals 2. And in that case, for any new phi, the number of operations can be calculated by this increase in 2 to the power of phi, or an increase in the order of 2 to the power of phi. So this permits us to be able to control the number of operations by just one parameter phi. And so as usual, we have a baseline model from which we start to increase its depth, its width, and its resolution. But since we're controlling all this just with this parameter phi, we can have this 2 steps. So with step 1, we first fix phi to be 1. So assuming twice more resources available and do a small grid search of alpha, beta, and gamma. So actually the writers of this paper did a grid search to find the best possible values of alpha, beta, and gamma based on equation 2 and equation 3. So based on this equation and this other equation right here. In particular, they find the best results for efficient B0 when that's the baseline model when alpha equals 1.2, beta equals 1.1, and gamma equals 1.15. And if you multiply these three, that's you have alpha, that's 1.2 times 1.1 squared times gamma squared, that's 1.15 squared. It's going to give you a value almost 2. And so after fixing these values for alpha, beta, and gamma, the authors scaled up the baseline model, which is the EfficientNet B0, using different values for phi. So they obtained now efficient B1 to efficient B7, and this was based on equation 3 as we have right here. Now taking a closer look at this baseline model, say here that its main building block is the mobile inverted bottleneck, that's MB-conv, which we can find right here, and we could find it in this paper, to which we add also the squeeze and excitation optimizations of Wu et al. Now this paper, which was referenced as the Sandler et al., happens to be the second version of the mobile net we had treated earlier. So we shall go directly into seeing exactly how this model is developed. From here we always have this depthwise, or we still have this depthwise separable convolutions which we had treated earlier, and then in this paper they introduce two other convnets, that's the linear bottlenecks and then the inverted residual networks. And if we take a closer look at this depthwise separable with linear bottleneck layer, we'll notice that we have this ReLU 6 instead of the usual ReLU. Now ReLU 6 simply means 6 is the maximum value the ReLU layer can give out. So if we have an input of say -1, as usual ReLU turns that value to 0, and if the input is say 2, the value is 2, and if the input is 24, the output is 6, because the maximum output is 6, hence the term ReLU 6. We also have this layer in which there is no nonlinear output. As you could see right here, we have after this we have ReLU applied, after this we have ReLU, but right here we have no ReLU, hence the term linear bottleneck. And the reason the authors prefer to use the linear bottleneck was simply because when you have this kind of input in lower dimensions, we'll see how much data is lost. So with this lower dimension, when dimension equals 2, we leave from this input to this kind of output. But as we keep on increasing the dimensions of the output and then projecting the results back to the 2D plane, we see that less information is lost. And so if we are carrying out an operation which involves transforming inputs into lower dimensions to avoid losing too much information, we could prefer to work with a linear activation instead of a non-linear activation like the ReLU, which will lose much information. And also experimental evidence suggests that using linear layers is crucial, as it prevents non-linearities from destroying too much information. Now for the next type of model, that's the inverted residuals, the bottleneck blocks appear similar to residual block, where each block contains an input followed by several bottlenecks, then followed by the expansion layer. However, inspired by the intuition that the bottlenecks actually contain all the necessary information, while an expansion layer acts merely as an implementation detail that accompanies a nonlinear transformation of the tensor, we use shortcuts directly between the bottlenecks. So unlike this residual block, with an inverted residual block, we have this expansion layer, which involves expanding, that's increasing the number of channels we have. So we could see it in the output right here. We have the depthwise separable layer which follows, and then there is this link between the bottlenecks. Also, the motivation for inserting shortcuts is similar to that of the classical residual connections, that's with the rest nets as we had seen previously. However, the inverted design is considerably more memory efficient. On this table right here, we can see exactly how a residual bottleneck block transforms inputs with k channels to k prime channels, with a stride of S and an expansion factor of T. So right here with this input of H by W by K, that's the number of channels, and with TK, number of 1 by 1 convolutions with the ReLU 6, we obtain this output, which is H by W by TK channels, hence the term expansion factor of T, since we leave from a number of channels of K to TK. And then the next we follow the depthwise separable, which is made of the depthwise and the pointwise convolution. For the depthwise separable, we see how this is maintained from TK to TK, and if we have a stride S, this H turns to H and the S, and W to W and S. Nonetheless, when S equals 1, H and W remain intact. And then from here, we take this output as input right here, we pass it through this pointwise, and we have an output of K prime. The others also specify that they use the ReLU 6 as the non-linearity because of its robustness when used with low precision computation. So the layer or the model block which was made reference to in the EfficientNet paper was this one, where we have our input, we have the expansion layer, and then we have the depthwise separable layer. Notice that right here we have this linear activation instead of the non-linear activation, which loses much data. It should be noted that when the stride equals 2, since the height and the width is going to change, we can actually link this 2. So that's why right here we don't have this residual shortcut link. And we can look at this, we see how this MobileNet version 2 was built using this bottleneck, as you could find here. And here we have the expansion T. So we move the expansion parameter varies as we go through the network. So we have here 1, 6, 6, 6 right up to the end. We have the conf, average pool, and conf. So with this, we've seen exactly the layer or the model which was referenced from the EfficientNet paper. The other part of the MB conf layers which was discussed in the EfficientNet paper was the squeeze and excitation networks developed by Hu et al. They are made of the squeeze and excitation blocks. We start with a squeeze block. In order to tackle the issue of exploiting channel dependencies, we first consider the signal to each channel, the output features. Each of the learned filters operates with a local receptive field, and consequently each unit of the transformation output is unable to exploit contextual information outside of this region. To solve this problem, we propose a squeeze global spatial information into a channel descriptor. This is achieved by using global average pooling to generate the channel-wide statistics. So after getting an output like this one, where we have, say, dimensions H, W by 6, since we have 6 different channels right here, we are able to extract just the information which characterizes the channel dependencies. And to do this, the authors of the paper propose to do a global average pooling. That is, once we have this input, say H by W, we get the average of all its values, and then we repeat for all the other channels. So each channel produces one value. The global max pooling was also tested, but the global average pooling happened to have better results. So this is the squeeze network, where we squeeze out this data from the channels. Then, to make use of this information aggregated in the squeeze operation that we just got, we follow it with a second operation which aims to fully capture channel-wise dependencies. To fulfill this objective, the function must meet 2 criteria. First, it must be flexible, and second, it must learn a non-mutually exclusive relationship, since we would like to ensure that multiple channels are allowed to be emphasized. To carry out this operation, 2 fully connected layers were joined together, with the first followed by a ReLU and the second by a sigmoid activation function. So from here, once we get these values, we pass it through a fully connected layer, and then after, another fully connected layer with a sigmoid activation. And all this is to extract the information from the squeeze block. More precisely, this block looks like this. So in the case where we have a residual network which goes this way with a shortcut, after this outputted value right here, we pass through the global pooling, which is the squeeze, the first fully connected with the activation and the second fully connected with the activation. Notice that this gives an output of C on R. So we have C on R hidden units, and then after this we now scale this back to give us an output which is the same as, or in the same dimension as, the output from this residual layer. Basically what happens here is we take back each and every of this output and multiply it with the corresponding channels. So we multiply with the corresponding features in each channel. So for this particular channel, we could take this value and multiply it. So if we have a value, say 3 right here, we'll multiply 3 with all these values. And then if we have 4 here, we'll multiply 4 by all these values, and so on and so forth. And that's how we get the output from the scale block. And then just like a normal residual block, we just link this input with the output. Now a combination of the inverted residual block and the squeeze and excite blocks gives this output, which happens to be the mobile net version 3 block. So there is a third version for the mobile net which has a block which is exactly this. That's a combination of the mobile net version 2 with a squeeze and excitation unit. So basically from this output right here, we do the average pooling, we get this fully connected, and then the rescaling for us to get this output right here, and then this moves to this output. So we're back to the EfficientNet paper. We have this MB-conf, which we've just seen exactly how it is built. We have this one to show the expansion parameter, which we had seen before, and then the filter sizes. And then we can see from the results that this more methodic and easy way of scaling up networks actually pays off in terms of accuracy. We could compare this to, that's the ResNet 50 with this EfficientNet B4. We'll see how they practically have almost the same number of parameters, but there is a great difference in the top 1% accuracy, as the B4 achieves an accuracy of about 83%, while the ResNet 50 an accuracy of about 76%. That's a great difference of about 7%, when the number of parameters of the B4 is even slightly less than that of the ResNet 50. And this is thanks to the fact that model scaling is done more efficiently. Practically, we shall see how the code for the EfficientNet MB-conf block looks like. Now, before going into that block, we shall look at the squeeze and excite layer. So let's develop the squeeze and excite layer. We start by the global average pooling, which now outputs this. So we now have this output shape of X. That's the shape of X is now of dimension 1, 1C. Since when we have an input, say, of dimension, suppose we have a dimension HW, that's HWC, the global pooling turns it to 11C. And then in order to prepare this input, that's this output right here, X, which is the input for the dense layer, that's a fully connected layer, we convert this, or we reshape this such that it's now of dimension C. Now that we have this dimension C, we input it in the dense layer, and then we have this output of the dense layer, which is of dimension C divided by R, as we saw in the paper, which is what we had seen here, where after the global pooling, we left from 11C to 11C divided by R, and after the ReLU, we turn back to 11C. And so right here, since we have this output, which is 1C, 1 divided by C, or rather C divided by R, we now take this to C. So this makes our output to be of dimension C. And then in order for us to multiply this output, that is each of these channels, with the inputs, that's this input right here, we need to reshape this X, or we need to reshape this X, which has this output C, or which has this dimension C, into a 1, 1, C dimension. tensor, such that we multiply it with x, or we multiply with the input, which is HWC. And now doing this, we are able to multiply each channel with the values contained in this last channel C. Then to construct the residual block, since we've constructed the squeeze excitation block, which was this, we have this 1x1 filter conv layer followed by a nonlinearity, then the depthwise layer followed by a nonlinearity, and finally this pointwise conv layer. So this tells us that the squeeze excitation block shall be introduced once we've gotten the output of this depthwise conv layer. Then if we look back at the mobile net version 2 paper where we had this defined and we had this input HWK, and then with the 1x1 conv layer and ReLU 6 we had the output HWTK, meaning we had TK filters. Hence, when defining the inverted residual layer, we take in the expansion factor T. And so when building this conv2D, we have this expansion factor T times K number of filters. The other filter size is 1, stride 1, activation, ReLU, and then the pattern same. But recall our activation is a ReLU 6. So we take this off, and then we define the ReLU 6. So here we have tf.neural_network.ReLU 6, which takes in this conv_d layer and then outputs its value after going through this ReLU 6 activation. The value of k is obtained by getting the number of channels of the input, and that's gotten by taking this last dimension of its shape. So that's how we get k. We've gotten t, and then we're done with this first layer. We now move to the depthwise convolution. There is this depthwise conv2D available in the documentation, which we have been using already. But then this is a depthwise separable, which means it's a mixture of the depthwise layer and the pointwise layer. Nonetheless, between the depthwise and the pointwise, we want to insert this squeeze excitation layer. So this means we can't use this layer that's given to us in the documentation. We have to go and use the depthwise convolution layer, which doesn't include the pointwise layer. So we're using the depthwise instead of the depthwise separable in this layer. So because of this, when defining our custom depthwise conv2D, there is a modification. Now we have this depthwise conv2D, which just does the depthwise. And then we have this batch norm. But unlike the functional API where we generally include inputs like this, now we have to pass this inputs in here. So we have this, we have the depthwise, we have the batch norm, which takes the output from this and then outputs it, and that's what we return. That's what gives our custom depthwise conv2D. The custom conv2D is the same as what we saw before. So we get back to this. We have this custom depthwise conv2D, which has filters 3x3, stride S, which we could define simply right here. So we could have S self.s equals S. So here we have self.s. Pattern same, and that's it. And now this input, or rather this output from here, will become the input to the squeeze excite layer. We've seen the squeeze excite layer already. We have R equals 1. That's for the case when R is taken to be 1. So yeah, we have this output gotten from the squeeze excite layer, which we had defined already. And then taking this output now, we pass it through the pointwise layer. The pointwise is a conv2D with 1x1 filters, and we can take k number of channels. So there we go. So with this, we've taken this pointwise, and then we have this output. We now add it up since we have that ResNet or that ResNet type connection, and that's how we output. And we're done with this inverted residual block. So once we're done with this, we just repeat this inverted residual block the first time, second, third, fourth, fifth, sixth, and seventh time. And that's basically how we build this. And with this, you could build it sequentially. using the sequential model which comes with TensorFlow. And then to build the other family of efficient nets, as we had seen, we simply vary the values of phi. We had seen how this varying was done. We simply vary phi using this alpha, beta, and gamma, which we had gotten already using the grid search. So using this grid search, these values were gotten. Now we value the values of phi, and we obtain the depth, the width, and the resolutions for each of the EfficientNet model. And so if we want to generate, say, this compound scale with z equals 1.4, width equals 1.2, and r, the resolution equals 1.3, we shall take the base and multiply its depth. So if we have, say, 14 different layers which are stacked, we shall multiply this 14 by 1.4 to obtain the number of layers for this new model, and then the number of channels, that's the model width, will be increased by a factor of 1.2, and then the resolution of the input images will be increased by a factor of 1.3. And once this is done, this baseline model is going to be increased accordingly. So we shall have an increase in the number of layers which is stacked, an increase in the number of channels, and an increase in the input resolution, which will obviously give better accuracy with a controlled number of operations.